When we try to probe the infinite, which is home to galaxies, nebulae and black holes, we tend to neglect our views. With that, we do not give due importance to our way of looking at these distant events, always out of date. We make an effort to leave subjective interpretations aside and try to stick to what we see from the outside, or what can be directly observed and measured. For those who follow Lord Kelvin's booklet, a deceased English physicist, what cannot be measured does not exist. The Images of the Universe series considers that all measuring devices, which we use to evaluate cosmological events, constitute appendices of our memory. These include our antennas and telescopes, or even our quantum clocks. It is our memory that will interpret the data obtained, and that will give the final word. A typical example of what has been said is the use of light and cosmic radiation as a tool to measure the time and distances that separate us from the stars. When it comes to astronomical distances, these variables are never measured directly, being the result of some form of remote tracking. For example, a star would not exist or could not be seen directly in the night sky until the exact moment when its light reached us. When that happens, the star's light, through its waves, could be followed by an antenna only in the direction of our past, and would show us the star as it looked thousands or millions of years ago. It is logical that this type of evaluation depends only on our points of view. For its part, the universe isn't too concerned about what we think about it. There is a risk and uncertainty in the use of light as a measurement tool, which many Images of the Universe videos strive to draw the viewer's attention to. We are referring to the need to consider, in the case of using light, that its waves would be continuous. Thus, when evaluated by waves of limited velocity, and not directly, space would merge with our notion of time, forming a space-time continuum. This stems from the fact that we can only measure the time, which separates us from distant stars, by the limited speed of light. There is no other tool available. Thus, Einstein's classic continuum, formed by space and time, would be incorporating a third variable, represented by light. What happened to light would also apply to space. If light bent, space would bend, and vice versa. This continuum would become false if there was any rupture that would affect the continuity of electromagnetic waves. We believe that this rupture exists, but it could not be directly detected by any experimental method. This is the necessary packaging or quantization phase of light energy, which is known to take no time. In his experiments with oscillators, Planck demonstrated that light would be quantized. Even so, he preferred to believe that light would travel through the vacuum in the form of continuous waves. To detect this break in the continuity of the waves, we would have to leave the dimension of time, which is impossible. Thus, it also becomes impossible to prove that the waves scattered by a free electron, when hit by a quantum of energy, would be discontinuous. The fact that we cannot measure the quantization time, if it existed, could have led scientists to an interpretive mistake, which is perfectly justifiable. At the moment of scattering, the quantum and the electron appear simultaneously, without any time interval having been measured so far. The fact that physics has already demonstrated that the formation of the quantum does not require time is a strong indication of the discontinuity of scattered waves. the waves would become apparently continuous from the observer's point of view by an access exclusion principle. That is, if in the light-packing phase time could not be measured, this would also happen with the particle's own movement. What would remain, in this case, would be the delayed scattering of light in the form of apparently continuous waves. We used to think that space would be able to bend light, and that might actually be true. However, the only tool available for evaluating the geometry of space is light. It seems to act in the form of a messenger from space. This confusion between the behavior of light and space constitutes a strong argument for concluding that science could have been induced into an interpreted error, which would have nothing to do with mathematics. The Doppler effect would also depend on the polarization of light. Ultraviolet and infrared should accommodate to the curvature of space as light waves stretch, placing themselves at opposite ends of the spectrum. The formation of the curvature of space, however, would have a negative nature, dragging light with it, and making light inaccessible directly. That is, the light would be there during the formation of the curvature of space, but it could not manifest itself to us. The transitory imprisonment of light in the space-stretching phase would be a natural consequence of the complementary contraction of time. The timelessness of the expansionary phase would coincide with what would be expected in the quantization phase, or the packing of light. Thus, the bending event, which would have polarized the light, could not be directly measured, as it would not involve any measurable time interval. Thus, in the inflationary phase, the universe would become virtually flat and static, just like scattered light. This curvature event does not exist from our point of view, because, due to the contraction of time, it would be virtually placing itself in our future. As whatever was in our future would not have happened yet, it can be assumed that the formation of the curvature of space would occur outside of space-time. If the light had been polarized undetectably, preparing for the delayed manifestation of the Doppler effect in spacetime, the light of a distant star should already appear depolarizing in the present, or shortly after the reversal of the arrow of time. But what you see directly is the polarization of its light being projected with a delay on the celestial vault. It is as if the depolarization of starlight in real time allowed the delayed registration of its own polarization through the Doppler effect. As a consequence, instantaneous exposure of light polarization would exclude direct recording of its depolarization, which would become a fictitious event. The two phases of the harmonic movement of light would become continuous and mutually exclusive. As long as one of them was there, the other would disappear. The polarization light record cannot be denied, as you see distant stars, as they did in the past. The redshifted light appears to be arriving from space, rather than from our position, after having transited through the subatomic level of our brain. Therefore, our biggest cosmological mistake was that we considered that light waves would be continuous. Interestingly, Einstein attested to this error when he made one of his most controversial statements. He suggested that, when traveling through a vacuum, light would use its particle aspect, not that of a wave. As a particle does not emit radiation in its corpuscular aspect, how could light travel in a vacuum? This statement by Einstein makes perfect sense and is consistent with the lack of time in our future. For example, light from Beta Andromeda takes 75 years to reach us. If the star went out now, we wouldn't know about it until 75 years later. Logically, there is an information void separating us from the star, even if we are seeing it shine continuously. Therefore, the future would be an illusion, resulting from only being able to look at the star's present as if we were in the past.